Welcome back, students. Today we approach what I personally consider the heart of electrostatics. Gauss's law is not just a chapter. It is a philosophy of symmetry. Most textbooks say, flux measures how many field lines pass through a surface. A senior physicist clarification, field lines are only visual tools, not real objects. The real meaning of flux is phi equals. It measures the component of the electric field that pierces a surface. Key points. If the field is parallel to surface, flux equals 0. If field is perpendicular, flux is maximum. Negative sign simply indicates direction. Flux tells us how much of the field escapes through a surface. The flux through a closed surface depends only on the net enclosed charge. It does not depend on shape, size, or location of charge inside. Gauss's law is exact, universal, and foundational to electrodynamics. A senior professor always explains, Gauss's law arises because nature uses inverse square forces. Why? Because the surface area of a sphere grows as 4 pi caret 2, and electric field weakens as 1/2. This perfect cancellation gives times 4 pi caret 2 equals constant. Hence, contour integral equals /epsilon_0. This is not coincidence. It is symmetry. A senior physicist emphasizes this rule. Gauss's law is always true, but it is useful only when symmetry exists. We use Gauss's law when the field has same magnitude on the Gaussian surface, has 0 degrees or 90 degrees angle with the surface, is constant over segments of the surface. The three symmetries. Spherical symmetry use spherical Gaussian surface. Cylindrical symmetry use cylindrical Gaussian surface. Planar symmetry use pillbox Gaussian surface. A. Electric field due to a point charge. Gaussian surface, sphere of radius, equals /epsilon_0, equals 1//2. We recover Coulomb's law, beautiful consistency. B. Field due to infinite line charge. Choose a cylindrical Gaussian surface of radius and length. Contour integral equals lambda/epsilon_0. Thus, equals lambda/. Senior insight. Notice the 1/ dependence, typical of cylindrical symmetry. C. Field due to infinite plane sheet of charge. Gaussian surface, pillbox. Enclosed charge equals sigma. Flux emerges from two faces. 2 equals sigma/epsilon_0. Thus, equals sigma/. Important remark. Field is constant, independent of distance. Only planar symmetry can produce such a field. D. Field of spherical shell. 2 regions. 1. Outside shell. Behaves like a point charge at center. Equals 1//2. 2. Inside shell. Equals 0. Reason. Every bit of charge pulls you, but the pulls cancel perfectly in all directions. This is a deep symmetry result, not a coincidence. A senior physicist stresses this. 1. Field inside conductor equals 0. If field existed, free electrons would move contradiction. 2. Entire charge resides on the surface. The conductor rearranges charges to reach equilibrium. 3. Surface charge density may be non-uniform, highest at sharp edges. Reason, curvature concentrates field. 4. Field just outside conductor equals sigma/epsilon_0. Direction, normal to surface. A conductor with a cavity. Net charge inside cavity induces charge on inner surface. Opposite charge appears on outer surface. Field inside the conductor's material remains 0. Expert insight. Even irregular cavities obey Gauss's law, but with modified surfaces, fields, and induced charges. A senior professor warns, they choose wrong Gaussian surfaces. They force Gauss's law into asymmetric problems. They forget flux is a dot product. They mix up flux and field. They apply spherical surface to line charge. They ignore which part of the surface actually contributes. Gauss's law is not difficult, but it demands respect for symmetry. Frequently asked, field of non-conducting versus conducting sphere. Cavity problems. Infinite line and plane. Flux problems with angles. Conical surface flux. Location of 0 field. Charge enclosed versus charge outside the surface. Gauss's law reveals the hidden simplicity of nature. When symmetry exists, the mathematics becomes almost effortless. Master the technique of choosing Gaussian surfaces, and the rest of electrostatics becomes a gentle climb.